Hello and a warm welcome from me. My name is Markus Sobach and I will present today our approach, stereo EKF post-based SLAM for autonomous underwater vehicles. First of all, the table of content of this talk. I will start with a short introduction, then I will continue with the mathematical background of the 3D transformation. Then I will go into detail with the image registration, and then I will put all the information together in the final chapter, which is the visual EKF SLAM chapter, where I will present our approach. After this, I will continue with the experimental results, and finally the conclusion. The problem statement. The accessibility of the subaquatic world is quite important for research and industry. This is mainly done nowadays by the usage of ROVs, so remotely operated vehicles. But they have some major disadvantages in comparison to the AUVs, so autonomous underwater vehicles. First of all, they are tethered. They are dependent, for example, to a support ship if we have a sea mission. And they are not self-powered like autonomous underwater vehicles. But the major question for autonomous vehicles in general is how to perform a precise localization. And this is the major task we are facing with this paper. So, first of all, you have to define the localization of the vehicle. We are doing this with the pose. So the pose consists of the position and the orientation, which is actually the vehicle state. If we have some vehicle states over time, as you can see here, at the initial state, the next state, and so on, you put this information together in a state vector, which is representative for the trajectory. So, we start at the initial point here, and we continue, we get some information. In our case, we get some information from the visual odometry, which is basically the displacement of two consecutive images. But this is first of all an estimation of the relative transformation. So, as we all know, sensors are prone to drift, and cameras are also sensors. So we need a periodical adjustment from time to time. We do this adjustment by the usage of SLAM. SLAM identifies regions we have already met in the environment before. So for example, if we have collected an image here, and at this position we find an image which has a certain overlap with a collected one from this date, we call this a loop closing. But I will show more details in the later chapters. So we do this redefinement, or we do SLAM by the usage of AKF, so extended Kalman filtering. The related work facing such problems are really scarce. But the main problems of them are the definition of the state vectors, as you can see here. Schatzschneider is putting also the landmarks to its states, and OSTs is building the state vector also with a lot of information. Further on, OSTs is running the image registration at every iteration. He's using the image registration to detect loop closings. In this study, to outline the main features, our state only consists of the poses, the landmarks, so the result of the image registration is stored in a separate vector and are not influencing the equations of the AKF. The orientation is represented in the quaternion space to get rid of the singularities. And the image registration can be run at every n iteration, so it depends. If you need a precise localization, you put this n to a lower number. If the localization can be more rough, then you can put a higher number. The 3D transformation. First of all, it's defined, in our case, with two functions, the composition and the inversion. So we start at the initial pose here. We get some new information of the visual odometry, which is shown here. For example, a displacement in x direction. In the first image, the mountain you can see on the right side. The next consecutive image, the mountain's on the left side. So we have a relative displacement of the camera in x direction. The visual odometry also provides us information about the y and z coordinates and roll, pitch, and yaw. This information, this relative transformation, is composed with the composition function to our state to get the next absolute state. Also, we have to calculate the covariance or the uncertainty of the upcoming state, because the system is prone to drift as we are using sensors. And this is done by the usage of linearization of these two functions, because the Doppler transformation is non-linear. The image registration. So now we've tried to find out how to detect the loop closings, what is really important for the whole approach. The image registration has as a result, if it's successful, a loop closing. So to every state, we are storing the images. At a certain state, for example here, at the current state, we run the image registration with every stored state in our image vector. And the result is that we have found the image registration between this state, so the state or the image of this corresponding state, and this image, which is corresponding to this state. The result is the relative transformation between the images between xk and x2. Because, as you see quite easily, they have a certain overlap. They're representing some area of the same environment. The pseudocode of the image registration looks like this. So we take into account the current stereo image pair, left and right, here marked as SL and SR, and one loop closing candidate, which is marked as IC. First of all, we translate such image into a feature set, FC. We are using SIFT at this point. The stereo matching, so now the matching between the stereo camera rig data is done by a composition of defined feature functions. So we describe SL and SR with two descriptor sets, FL and FR. And then we are able to compare each element of the feature sets with each other. And if the differences reaches a certain threshold, we can call such features as matched. The result can be seen in this image, A. But you also see that we have some outliers here, so some wrong matchings. And we are using RANSAC at this point to redefine the solution. The result can be seen here in B. So we have now described SL, SR and the loop closing candidate with feature sets. And the next two lines, line 3 and 4, are used to align every feature set with each other. This means that the first feature of FC corresponds to the first feature of FL, and the first feature of FL corresponds to the first feature of FR, and so on. This is quite important for the next steps. I continue now with line 5. Line 5 is calculating from the stereo image information the 3D point sets P3D by the usage of the reprojection matrix and the disparity. Now we have all information together to finally calculate the relative transformation in the function solve PMP RANSAC. We are solving this problem by solving the perspective endpoint problem. We have now the 3D points, which I calculated from these two images actually. This is only the left one from the stereo image rig, and these 2D data from this loop closing candidate. The result is an estimation of the post-transformation, which is minimizing the reprojection error between the 3D feature set here and the 2D feature set here. And the result is the relative transformation. So we have found and detected one loop closing. So we have now all information together. We know how to add new information to our states, and we know how to detect loop closings. Now we can put all the information together in the AKF SLAM chapter. AKF is mainly done with 3 stages in our case. First, the prediction stage, the augmentation stage, and the update stage. The prediction stage is only getting the last state of the state vector and the corresponding covariance matrix to this state. With the new odometry data information from the visual odometry, we are composing now the odometry with the current state to get a new state prediction. The calculation of the covariance matrix, so the uncertainty of this state, is calculated by the application of the Taylor series of the first order, as can be seen here, and the result is the corresponding covariance to this state. In the augmentation stage, this is the more simple stage of the AKF SLAM. We are just augmenting the state vector by the new estimated state and the global covariance matrix by the corresponding covariance. The update stage is now the more tricky one, and here is where the magic goes, because this is highly dependent on the image registration. If we don't have any image registration, so no loop closing was detected, we skip this stage and we wait for the next iteration, so no update is performed to the whole trajectory. In our case, we have now found a loop closing again between xk and x2. Now we calculate the observation function h, because we need a comparable result, and in our case, this is now done by taking into account the information of the state vector. We are now going minus xk, this is the inversion function of the 3D transformation, plus x2 to get the relative transformation between both states. This can be seen here. So remember, hk is calculated by the usage of the state vector, and zk was calculated by the usage of the corresponding images to such states. So we have now two comparable results, which are important in the next step by calculating the innovation. The innovation is calculated now between these two, and in general, it tells us the differences between h and z. So the result of the image registration and the result of the observation function. For the translation, you can just calculate the differences by subtracting the translation part of these relative transformations. But as we are dealing with quaternions, to express the orientations, we have to deal with some special things. Because different quaternions can express quite similar orientations. So the solution was to use absolute values to express the differences between both orientations. So the rotation, or the innovation of the rotation, is done by subtracting the modules. We have now covered all important steps of the update stage. All following stages are just standard application of the extended Kalman filtering, and I will skip them at this point, and I will refer to the paper. The experimental results. We use a standard laptop to run the system, running Ubuntu 12, and the implementation was done with MATLAB. The implementation runs only on one single CPU core. The setup was this autonomous underwater vehicle developed by the University of the Balearic Islands. The mission was recorded in an underwater tank, and the ground truth couldn't be easily derived because at the ground of the water tank we had a digital printed seabed image, and we could do the image registration with the observed images of the camera with the original digital image. The test was a 23-meter sweeping task with 6 different noise levels. Why the 6 different noise levels? We pulled them because we wanted to know how the system reacts to more corrupt odometry. The error definition is the difference basically between the ground truth and odometry, and the ground truth and AKF SLAM, divided by the length of the trajectory of the ground truth. And finally, we got the error units, what is meters per traveled meter. So here are the quantitative results. With a noise level of 1, what is basically no corruption of the odometry at all, AKF was already improving the trajectory by 28%. With a noise level of 4, for example, the odometry error was around 80 centimeters. AKF was correcting this to 30 centimeters, what brings us an improvement of 61%, and so on. This behavior is quite typical for AKF. So as the data gets worse, but AKF is only increasing, so the error of AKF is only increasing slightly, and the improvement increases. As I told you, STs was using the image registration at every iteration. And we had a built-in function that you can set your own iteration number, and we have found out that already with a separation of 4, we have still reliable and good results, and the execution time of the system was already faster than the mission time. Here you see finally the trajectory. In black, the original odometry. In blue, the ground truth, how the vehicle was actually moving. And in red, the AKF result, so the corrected black one, if you want to say like this. Magenta lines are the detected loop closing or the used loop closings for this mission. With a noise level of 4, the visual odometry gets corrupted and is drifting a lot, but still AKF is correcting this close to the ground truth. Noise level of 6, so the highest noise level. The visual odometry is more or less useless, but the AKF system is correcting this pretty close to the ground truth. Now I will show a short video of the system. Blue again, the ground truth. The red line is actually also the black line, so visual odometry and the AKF slam are still perfectly aligned. This is due to we don't have any loop closings found yet. The first loop closing is detected now, and after the update stage, both trajectories are different. The next loop closing, you can easily see, it will appear in a few seconds, that AKF is snapping towards the ground truth. I will skip some seconds. The next loop closing, this was a big update. I'll go to the end. And you see, visual odometry ends somewhere in the nirvana. And the corrected one will end also not exactly at the ground truth, but pretty close. So, the conclusion. We presented a post-based visual AKF slam approach for vehicles actually with up to 6 degrees of freedom, but we were only testing it with vehicles or with autonomous underwater vehicles, so just theoretically. We are using only stereo data, and the orientation was represented by the usage of quaternions, so in the quaternion space. The state vector again only consists of the poses, and with a separation of 4, the execution time was already under the mission time. Thank you very much for your attention, and now we have plenty of time for questions.
Thank you, Marcus. You're right, we have time for questions. Are there any?